Hi everyone! Today we are going to learn elementary set operations. In this video, we are going to define and perform the union, intersection, and complements of set. We are going to exhibit properties of set operations, and then we are going to prove De Morgan's law for sets. So if you're ready, halina't matuto. To visualize the set operations, we are going to use Venn diagram. For any object X and any set A, only one holds a time. Either X is in A or X is not in A. So to visualize that in Venn diagram, we can use this circle to represent the set A. So everything inside the circle will be an element X inside A, and everything outside is an element X not in A. Now, if we have two sets, so what are the relationship of X in these two sets? First, we know that for any element or any object X, there are two possible scenarios. Either X is in A or X is not in A. And only one of the two is true. Now, with respect to another set, say B, we have the following scenario. If X is in A, then with respect to B, either X is in B or X is not in B. Similarly, if X is not in A, you have the two scenario, either X is in B or X is not in B. So for any object X, you have X is in A and X is in B. So that's one possible scenario. Either X is in A and X is in B. Or if X is in A, the other possibility is that X is not in B. So X is in A and X is not in B. So those are the two cases when X is in A. Now when X is not in A, you can have X in B, or you can have X is not in B. So all in all, you have four possible scenarios for any object X and any two set A. To visualize that, we can use the following Venn diagram. So let's say that everything inside this figure is set A and everything inside the next period is set B. So the first case involves all sets coming inside of A. And these elements are split into two scenarios. Either within A, X is in B as well. So this is scenario 1. Or within A, X is not in B. So this is scenario 2. The next set of scenarios is derived when X is not in A. So we're talking of everything that is outside A. So what are those? Either those are the elements that are inside B. So this is scenario 3. Or outside C, outside B as well. So anything outside both A and B gives us scenario 4. So all in all, those are the four possible scenarios. Of course, it will be a good exercise if you can try yourself when you have any object with respect to three sets. So from here, you can extend that each of these four cases will extend to or will give you two more cases. Either X will be in the third set or X will not be on the third set. So you just have to draw a Venn diagram with three sets. So the regions that was created using these three sets will be determined by the cases which will evolve from these sets. So now let's talk of the first set operation, union. By definition, the union of the sets A and B is the set of all elements which belong either to A or to B or to both of them. So here, we have two sets A and B. So the set, either an object belongs to A, so that means it is also in the union, or the object belongs to B, or to both of them. It's both in A and B. So we write that as follow. All object X such that either X is in A or X is in B. The or here meaning the logical operator or. So in logical operator, the or means the and or the inclusive or. Meaning it can be in X or it can be in, meaning it can be in A or it can be in B or it can be on both of them as we've seen in the Venn diagram. Let's have some example. Let's say we have the set A, B, C, D for A, the set containing B, D, F, H for capital B, and the set containing C, D, E, F as our set C. So to get the union, all we need to do is to get all the elements of A and then combine it with all the elements of B. So all the elements of A are A, B, C, and D. And then the elements of B are B, D, but B and D are already in our list. So all we need to do is to include the other elements of B not already in our list. So that will give us F and H. So these six elements are the elements of the union. Observe that this is the same if you get the elements of B first. Let's say the element of B are B, D, F, and H. And then you combine it with the elements of A, which is A, B, but B is already here. So A, B, C, and D. Take note that the set, in the set, the ordering of the elements in the list does not matter. So for as long as they have the same elements, then the set are equal. Now, A union C, the elements of A again are A, B, C, and D. And then for the set C, you have C, D, E, and F. So you need to include E and F as well. Now, similarly, this can easily be shown that this is the same as C union A. And finally, B union C is we list the element of B, so B, D, F, and H. And then you get the element of C. So that's C, D, D is already there, so including C, D, E, and then F is already in the set, so we close the set. So those are the element of B union C, which can easily be shown to be the same as the element of C union B. We can actually summarize these properties as follow. So let's talk of the properties of the union and then let's prove each property using the definition and some technique in logic. First property. For any sets A, B, C, and D, the following hold. For the first one, A union A is the same as A. Intuitively, this is rather obvious already A union A, meaning you're going to get all the elements of A and then you're going to combine it with all the elements of A. Since we're talking of the same set A, then the result must be equal to A. So how do we show that mathematically? So to prove it, we state for every X. So since we want equality between the left hand side and the right hand side, remember, to show equality of set, all you need to do is to show that they have the same elements. So recall, A is equal to B if and only if every element of X which is in A is also an element of B. And every element of B must also be in A. So that's how we prove equality of sets. We show that every element of A is an element of B and every element of B is an element of A. Now, this time, our left-hand side is A union A. So by definition, X is in A union A if and only if X is in A or X is in A. So that's from the definition of union. Now, going back to the property of logic, logic is idempotent. The operator or is idempotent. Meaning, if you have a statement P or P, then that's equivalent to the statement P. So this is just the statement X is in A. So we started with X being in A union A and we end up with X is in A. Therefore, we conclude that the left-hand side, since this is an if and only if statement, is the same as the right-hand side. And we are done. Now, we can also show that the union is commutative, meaning, as we've shown a while ago, the operation A union B is the same as B union A. And that's called the commutative property of union. So again, all we need to do is to state the proof mathematically. So for all X is in the union A union B, if and only if, by definition of the union, that means X is in A. Or, again, that's an exclusive or inclusive rather, that's an inclusive or. So either X is in A or X is in B. Definition of union. Now, going back to properties of logic, we know that this is the same as saying that X is in B or X is in A. Again, because the logical operator or is commutative. To recall again, P or Q is the same as Q or P. So if you remember, this is our symbol for the logical operator or. Now, applying the definition of union one more time, we can see that this is the same as X being in the union B union A. That's the definition of union. So we started with X being an element of A union B and we end up with X being an element of B union A. So we can therefore conclude that A union B is equal to B union A. And we are done. Let's continue with the third property, associative property of the union. So associative property means that whenever you have three sets and you want to combine or operate them using set union, so you can combine B and C first, B union C, and then combine that with A. Or you can combine A and B and then the result combined with C. So associativity means you can change the order of the grouping. So how do we show it? Again, since we want to show equality of sets, we are going to find, or we're going to show that every element of the first set is an element of the second set and vice versa. So for every x, what do we mean by x is an element of A union quantity B union C? So by definition, that means that x is in A or x is in the union B union C. But applying further the definition of union, so that will give us x is in A, or the compound statement x is in B, or x is in C. So both of this statement is due to the definition of union. Since we have a statement x is in A or quantity x is in B or x is in C, going back to our rules in logic, this is the same as associativity of logic. Specifically, the logical operator or. So meaning we can change the grouping of the logical operation from x in B or x in C to x in A or x in B. So you can think of them as three statement P or Q or R, which is the same as the statement P or Q and then or R. So that's associativity of the logical operator or. But the first group means that X is in A union B. So let's just copy X is in C. Now, another application of the definition of union, since either X is in the first set or in the second set, we can say that X is in A union B, the first set, union the second set C. Both of them coming from the definition of union. And therefore, we can say that since X belongs to both set, then those sets are equal. So A union quantity B union C is equal to quantity A union B union C. And we are done. So we are just using here the definition of set equality. Another property, A is a subset of A union any set B. Similarly, B is a subset of the same union. We will prove the first one and we will leave the second one as an exercise. This is an exercise. Exercise are good practice for you to reinforce the concept we learned here. So how do we prove that A is a subset of A union B? Recall again the definition. Very easily to see that a set is a subset of another set, all you need to do is to show that for all x in the first set, so if x is in the first set, then you should be able to show that x is also in the second set. So that's how you prove inclusion. Now, from the given, we want to show that A is a subset of the set on the right. So we start with the left-hand side. So for every x, what does it mean for x to be in A? Now, we can't say much about A, but using logic, we can use addition rule in logic and say that this statement x is in A or any other statement. In particular, we can add a statement X is in B. Again, that's addition rule in logic. So if you have statement P, therefore you can have statement P or any other statement Q. But this statement means that either X is in A or X is in B, or that means A X is in the union A union B. So that means whenever X is in A, X is in the union. This is only a one-sided implication. So this is not an if and only if statement because of the rule of inference addition rule. So we have A to be the subset of A union B. And we are done. Again, this second statement is the definition of union. This is a very interesting statement. A union empty set is A. So we have a set A and we are going to include the elements of the empty set, but we know that empty set contains no element, so no element were added. So that's the same as the original set A. But of course, we still need to prove it mathematically. Remember again by our previous statement, A is always a subset of the union including A. So whenever the union includes A, then A is a subset of that union. So from this to equality, we can easily see that A is a subset of A union empty set. Again, this is a general statement, statement 4. A is a subset of A union B. B is any set. In particular, we can get the set B equals empty set. So this is from property 4, taking B to be the empty set. So any general statement is true for a particular statement. Now, we only need to show the other inclusion. All we need now to do is to show that A union empty set is also a subset of A. So how do we do that? So this is what we want to show. So we're already done with the first inclusion that A is a subset of the union. So this time we're going to show that the union is a subset of A as well. So what does it mean for an X to be an element of the union? So A is an element of the union if and only if by definition A either X is in A or X is in the empty set. Now, X is an empty set, as we all know, is a false statement because any object is not in the empty set. So again, another rule in logic, disjunctive syllogism. So the first statement is true because of the definition of the union. Now, using disjunctive syllogism in logic, so if you have P or Q, but not Q, therefore, we have P. So since Q is not true, then it must be that X is in A. So we start with the, sorry, this should be an if then statement only because this is a rule of inference. So if P or Q and not P, then we have therefore P. So from our statement, X coming from the union means X is in A. So therefore, by the definition of subset, we have A union empty set to be the subset of A. So we have two-way inclusion, the first inclusion and the second inclusion, therefore, they are equal. And we are done. Again, some of these properties might be obvious already since we already encountered them in some math subject like algebra or lower mathematics. But here, our goal is to prove the statement using mathematical logic and definitions of sets and subsets. And of course, the operations involved. Let's have another property. If A is a subset of C and B is a subset of D, then the union of A and B is a subset of the union of C and D. We can visualize it using the Venn diagram. So we have set A, which is inside set C. So let's say this is A, which is inside C. Now let's say we have another set B and set D, where B is contained in D. So let's say we have this set B, but this B here is contained on a bigger set, let's say D. So the union of A and B, so this set here, is a subset of the union of C and D. Well, we know that the union of C and D is the whole set here. So the C and D contain, indeed, it contains the union A union B. So this is A union B, and then the bigger set outside, including of course the interior. So everything inside, that's C union D. So how do we do that? So we just have to show that this set here is a subset of this set. So all you need to do is to get an x from here and show that any x here is also in the second set. So for all x, what do we mean by x is an element of A union B? By definition of the union, this is the same as saying that either x is in A or x is in B. Definition of union. Now, since x is a subset of A, I mean x is an element of A, and A is a subset of C, we have a given. So that would imply by definition of subset that x is also in C. Now, on the other hand, we have x is in B, but B is a subset of D. By definition of subset again, then x must also be in D. So that's using the given and the definition of subset. By definition of subset, this is now just an if-then statement, not an if and only if statement. But what does it mean to have x is in C or x is in D? So that means that x is in C union D. That's the definition again of union. So we start with x being in the first set and end up with being on the second set. Since this is an if-then statement, not an if and only if, therefore we have A union B to be a subset of the second set C union D. So now, those are the simple properties of union. In the next video, we are going to discuss the next operation, intersection. This is a continuation of our discussion on elementary of set. So here we are going to discuss the intersection. First, let's define what we mean by intersection. We have set A and B. The intersection of the sets A and B is the set of all elements that belong to both A and B. So all we need to do is to get the common element of A and B. Mathematically, we write that as follow. A intersection B is the set containing all object X such that X is in A and X is in B. So this end here is the logical operator end. So in symbol, we write that as this symbol end. To visualize, let's say we have the set A and B as follow. So everything that is both in A and in B. So that means the region where both A and B overlaps. So that's our intersection. If the intersection of A and B is empty, then the set are said to be disjoint. So we can have the scenario where A and B does not overlap. So we call this set disjoint set, meaning the intersection is empty. So the two sets contain no common elements. Let's have some example. We have the same set that we use in the union. So let's say we have the set A containing the letters A, B, C, and D. The set B containing the letter B, D, F, H. The set C containing the letter C, D, E, F. So to get the intersection of A and B, all we need to do is to get the common elements. For A and B, so the elements of A are A, B, C, D. The elements of B are B, D, E, B, D, F, H. So the common elements are B and D. So we have A intersection B equals B and D. Of course, it can easily be shown that this is the same as B intersection A. A intersection C. So the common elements of A with C. C contains C, D, E, F. So those are the letters C and D. So the intersection of A and C is C and D. And similarly, we can easily see that this is the same as C intersection A. Lastly, B, D, F, H, and C, D, E, F, the common elements are D and F. So we have intersection of B and C is the set containing D and F, which is the same as C intersection B. We can easily summarize the properties of intersection, which is analogous to the properties of union. So we have, for any set A, B, C, and D, the following. A intersection A is A itself. So meaning, what are the common elements between A and itself? Of course, the whole set. A intersection B is the same as B intersection A, meaning uh, intersection is commutative. So both union and intersection are commutative set operations. Intersection is also associative. A intersection quantity B intersection C is the same as A intersection B and then get the intersection with C. So all of these properties are analogous to the property 1, 2, and 3 of the union that we've seen in the previous video. Now, A intersection B is a subset of A, and A intersection B is also a subset of B. If we look at the Venn diagram of A intersection B, so let's say that this is the set A and this is the set B. We can see that this intersection part here is member of the left set, which is A, and member of the right set as well, which is B. A intersection empty set. So what are the elements common with A and empty set? Of course, since empty set contains no element, so the common element is nothing. So the intersection of any set with the empty set is empty. If A is a subset of C and B is a subset of D, then the intersection of A and B is a subset of the intersection of C and D. So this is the same as our illustration in the union. Let's say that A is contained in a bigger set C. and B is contained as well in a bigger set D. Let's say this is C and this is D. So the intersection of two big set C and D is this one, and we can easily see that it contains A intersection B. All of these properties can be easily shown to the using the same technique that we use in the union. So the proof will be left as an exercise. Again, this is a good exercise or practice for you to reinforce the concept that you've learned. And this is also to show that you understood the concept of proving. Now here, what you're going to use are properties of the logical operator, and since intersection is defined using the logical operator and. So what if we combine these operations? What if we have union and intersection at the same time? So now we go to distributive law. So what is distributive law? This is the same law that we use or parallel or analogous to the law of distributivity of addition or distributivity of multiplication rather with respect to or over addition. But since we are defining intersection and union using the logical operator and or, this is the exact equivalent of the distributive law in logic of addition and rather logical operator and logical operator or. So first property, A intersection quantity B union C is actually the same as A intersection B union A intersection C. So if we look at the statement, this is A intersection and then you distribute that to B. So you have A intersection B. You distribute it to C. So you have A intersection C. And then whatever the operation is between B and C, that will be the final operation. Now doing the same with A union B intersection C, you're going to distribute A union, so A union B, and then A union C. And then the final operation will be whatever the operation between B and C. Again, these two are just the exact equivalent of the logical operator and or. So for the first one, we can use the statement P and the statement Q or R. In logic, we know this to be equivalent to P and Q quantity or P and R. So we are distributing and over or. On the other hand, you can also have P or quantity Q and R. Here, we are distributing the logical operator or, so we have P or Q and P or R. So you're distributing P to Q and to R, and then the final operation will be AND. Okay? So that's distributive law in logic, and this is the equivalent distributive law in sets. So let's prove number one. For all x, what does it mean for x to be in the intersection of A and B union C? So that means that x is in A and x is in the intersection or in the union rather. So again, that's simply a definition of the intersection. Now, on the other hand, we have B union C. So that's, let me copy x in A. And so this is the compound statement x is in B or x is in C. So this time, that's the definition of the union. But now we have the logical statement P and Q or R. So we can now use the distributive law of and over or. So by distributive law, we can write it as follow. This is actually the same as x is in A and x is in B. So we're distributing this statement, or the other statement is x is in A and x is in C. Again, that's from distributive law of logic. But this compound statement can be simplified as follow. X is in A and X is in B means X is in their intersection. On the other hand, the second group, X is in A and X is in C, means that X is in their intersection as well. That's a simple definition of intersection. But since this is an or statement, that means that our X is in the quantity A intersection B, A intersection C, union of the two. That's the definition of union. So we start with the first set and then end up with the second set. So meaning every element of the first set is in the second set and vice versa. So that means that the two sets are actually equal. So A intersection B union C is the same as the quantity A intersection B union A intersection C. And we are done. The same can be done for the second rule. So the second rule for distributive law will be left as an exercise. In the next portion, we are going to discuss set complement.